This is a short tutorial on video on the Cape Cod Canal. We're going to be looking at some model results to examine the velocity field and circulation in the canal. Just to start off, some basic dimensions on the canal. Shown in the map here is the canal which connects Buzzards Bay here to the west to Cape Cod Bay here to the east. The length of the canal from the exit here into Cape Cod Bay from the Maritime Academy here is about 12 and a half kilometers. The width of the canal is about 200 meters, a bit more. So it's long and narrow, and the depth of the canal is the main channel is dredged to about 10 meters, although it varies. It's all greater than that, but varies along the canal and with the canal width. So the aspect ratio of the canal is roughly 200 meters wide and 10 meters deep. So about 20. The canal is curvy, so you can see here there's a curve bend right here. The radius of this curvature is fairly short. It's about 2.5 kilometers, and that curvature affects secondary circulation that I'll talk about in a second. By convention, the canal, the flood direction is west to east, so this is defined as flood from the west side towards the east. So the current vectors you see right now are in an ebb situation. The influence of the Earth on the canal in terms of the Coriolis effect is small. It's quite small. Even in the cross canal circulation, the secondary circulation, it's a rather small term compared to curvature effects. It will be it's in the model, the results I'm showing, but the importance of the Earth's rotation is quite small in this system. The canal features very strong currents, peaking over 2 meters per second. The primary reason for that is surface elevation forcing. So it essentially connects, it was cut through to connect these two bodies of water here, allowing transit through this without having to go around the cape where all the shoals are. And these two bodies of water have very different tidal signals. Buzzards Bay has a much smaller tidal variation. The dominant constituent on both sides is the semi-diurnal, or M2 tidal signal, which has a period of just over 12 hours. On the Buzzards Bay side, the amplitude of that signal is about a half meter. On Cape Cod Bay, the amplitude of that M2 period is about 2.25, a bit more. 1.25, a bit more meters. So it's quite different. It's more than a factor of 2. Also contributing to the surface elevation driving the system is a phase difference. So high tide here in Cape Cod Bay lags high tide in Buzzards Bay by about 3.5 hours. So that lag induces a difference in elevation, which is what's driving this flow. So the flow through the canal is driven by this pressure difference. The pressure difference stems from difference in water elevations on either side, with the elevation on the Cape Cod Bay side oscillating about 3.5 hours behind, and with much greater amplitude than the Buzzards Bay side. And this leads to a difference. So that's shown in this elevation plot down here. This is time. This is essentially an arbitrary section of time. It happens to be June 2009 across a spring tide, neap tide, larger spring tide cycle. And on top of that, you see the daily variations in the sea surface height, the red being the Cape Cod Bay side and blue being Buzzards Bay. So you see the range in Buzzards Bay is much smaller than Cape Cod Bay. And importantly, the difference between them. So this black dot shows at an instant what the elevation is in Cape Cod Bay, and the blue triangle is the sea surface elevation in Buzzards Bay. And it's that difference between them that's what's driving the flow. This represents this instant right here where we have higher elevation in Cape Cod Bay, shown by that black dot at about a meter above sea level, mean sea level. And in Buzzards Bay side, you're about a half meter below mean sea level. So there's almost more than a meter of difference between these two sides. So the elevation is about a meter plus higher than it is on this side, and that tends to drive a flow downhill, which is counteracted by frictional losses such as bottom friction and lateral friction and wall roughness, eddy-making losses inside the canal. Principally bottom friction is the biggest energy dissipation term in the canal, and it's rather strong. So it's the difference between these dots that really matters when we go and show a time series, and we'll see that the sign of the difference changes. It's at times Buzzards Bay is higher than Cape Cod Bay, which means that water will flood in the other direction, and the flood sense. At times they are the same, and the currents are nearly in phase with that tide difference. So the adjustment time scale is quick because of the bottom friction in the canal. That head variation varies from 0 when they are exactly the same to over 2 meters. At times of the month down here, when we get into these big spring tides, there can be 2 meters difference between the two bodies of water. So what I'm going to show you are results from a model. This is an oceanographic model. It's a three-dimensional model of the circulation in the canal, specifically set up to look at tides and tidal energy, tidal power potential of the canal. This is just one of the multitude of models that we have. This one just is good for looking at the results. The domain of the model is bigger than what's shown here. It extends into Buzzards Bay, into Cape Cod Bay, and what is done is we take the domain of interest where the water is, and we tessellate it into in the horizontal sense, into lots of little triangles. Each triangle gets down to about 10 or 15 meters on a side, and then we have stacks of those triangles in the vertical, creating prisms. So there are triangles on one side and straight edges in the vertical sides. That's the shape of a prism. So stacks of prisms, 10 stacks of prisms, are used to break up this domain into little chunks, and those little chunks are non-overlapping, and we refer to them as control volume. And in each control volume, where FVCOM, which is the finite volume community ocean model, solves the conservation equations of momentum in each control volume. And conserving momentum, essentially you're solving for and advancing the momentum equations, which stem from Newton's second law applied to a fluid system, and gives you predictions of the velocity in every triangle, or every prism I should say, at every time step as you march forward in space. Here the velocity field again is primarily driven by pressure gradient, local advection terms, and bottom friction in a system like this. So I'll show you the results of this. The model, we call this model barotropic. We're not considering density differences. Cape Cod Bay and Buzzards Bay do tend to have density differences. For example, in the wintertime, Buzzards Bay will become colder than Cape Cod Bay because it's shallow and it's more responsive to the heat flux or heat losses in the bay. In the summer, it tends to be warmer. So there are density differences in the fluid that's washing back and forth through this canal. And those density differences in general can cause currents to form, but that forcing of the currents in a system like this is incredibly weak compared to pressure gradients and friction and other terms that are really controlling the velocities. So we can ignore them. This model is a constant density model. And as I mentioned, it does include the Earth's rotation, but it's a very minor, a negligible effect on a system like this. Because of this space-time scale and the rigorous currents in the system. So what I do is start it up. We can have a look at the results. I'm showing a few things. These vectors show the surface currents, and you'll see they'll evolve to slow down and then turn, switch direction over the tidal cycle, the semi-diurnal cycle. Each of these vectors, the length of the vector is essentially the distance a water parcel at that moment in time, starting from the tail of the vector, would travel over the next 3 minutes, I believe. So that gives you kind of a scale of the problem. I'll note here that the tidal excursion, meaning if you put a parcel of fluid here over a tidal cycle, how far will it travel? It actually, the distance it travels is about twice the length of the canal. So what we call a tidal excursion is about double the length of the canal. So it's on the same order as the canal, and that has implications of mixing between the two bodies of water from the tides. I should also mention along those lines, I am forcing the system with tides only. On top of this tidal flow, you can have what's called a residual flow, which is driven by mean differences or long-term varying differences in the sea surface elevation. For example, if a windstorm comes, it happens to increase the sea surface elevation in Cape Cod Bay, a type of storm surge. and not influence or negatively influence Buzzards Bay. That means on top of these tidal varying sea surface elevation signals is a longer term variation signal, and that long term variation, say days, on the order of 2 or 3 days, can drive a weaker flow underneath this tidal flow in one particular direction, and that can also lead to exchanges of materials, organisms, waters between the bay. Up here in this transect, actually let me start with this one right here. So this again is the elevation in meters, red Cape Cod Bay, blue Buzzards Bay, and then this again that's not important. What's important is the difference between them, which is the distance between this black and blue line. When the black dot is higher than the blue triangle, the Cape Cod Bay is higher than Buzzards Bay, and we're in an ebb situation. When the blue triangle is higher than the black line, we're in a flood situation, west to east flow. This shows right here a transect. I picked this transect in the middle of the bend because it's sort of the most interesting in terms of secondary flow. It's roughly halfway down the canal, so it has less asymmetry. There tends to be some asymmetry to the currents on either side here. The symmetry sort of weakens when you get in the middle of the canal, and we have this what's seen here is as if you're standing in the canal looking west. So you're standing right here, the cursor is looking in the water column, a slice of the water column, and that's what you're seeing right here. So this is the Cape Cod side to your left, the off Cape side up here to your right. This is the velocity passing through or normal to that transect in meters per second. It oscillates between positive and negative values. Negative values, as you see here, minus 1.5 meters per second, and these are contour lines. So this is along this line, the velocity is constant at minus 1.5 meters per second, minus 1.25 meters per second. And you can reference the color map over here to get a sense of blue. Dark blue is about minus 2 meters per second. Minus is ebb, as you see in this situation, heading towards Buzzards Bay. You'll see this evolve to red when it moves to the flood currents. Again, this is flow through, directly through, which is essentially the velocity, through this transect. The flow, because the canal is quite narrow compared to its length, even compared to this radius of curvature, the flows are largely constrained to moving along the canal. And this is the cross canal distance. I've centered it roughly towards 0. This is an arbitrary axis here, except the units matter. So you see about 200 meters of width. And then the depth is shown here down to 10 meters, again, is roughly the controlling depth of the canal, so a lot of the canal is below that. And then critically, I've rescaled this figure by a factor of 2. If the scaling were the same in the sense that the x-axis and y-axis have the same scaling, it's a little bit thin and difficult to see. So I've bloated it in the vertical direction. So just be aware this isn't exactly what the cross-section would look like. It's bloated by a factor of 2. This section up here is the velocity field within this transect. Most of the flow goes through. There's a slight variation within the transect, which is what you're seeing right here. And again, left is Cape Cod, right is off Cape. The rendering here is the lateral velocity, the sideways velocity in the canal. And the vectors show the full velocity field, including vertical components in the canal. And what you see, the evolution of this is this pattern, which just weakens and strengthens and weakens and strengthens, but it doesn't flip-flop. It doesn't change sign as it would due to a Coriolis effect, where you have a symmetrical signal that jumps back and forth. Here, as the ebb moves to flood, the Coriolis acceleration changes sign, so we flip-flop this pattern in the canal. Here you see the pattern stays the same. The surface currents tend to move from the Cape Cod side to the off Cape, so that's moving from here to here, and the bottom water is a return flow moving from the the off Cape side back to Cape side. You see this right here. So it forms sort of a circulation pattern like this, and this is typical of a bend, even in a river, where you have the water moving out here and back here. It sets up a pressure gradient. Basically, the water's a little higher on this side than it is on this side, and that pressure gradient overcomes the flow at the bottom and tends to push it back, and you have in the net a circulation that looks like this. These secondary flows are quite weak. They're on the order of, I don't know, something like 5 centimeters per second, maybe a little bit more, compared to 2 meters per second of the along canal flow. You're talking a factor of 20 to 50 weaker. So secondary flows are weak, but they can have implications. So it isn't going to throw a ship off course, but can have implications in terms of scour, changes in the morphodynamic changes in the canal, and the Corps, of course, does regular surveys of the canal. And I should mention actually that the bathymetry from this was a very critical piece of the puzzle of developing a model. Bathymetry is very important. Came from an Army Corps of Engineers survey from, I believe, 2011. So they go out and survey the canal, and that data is used to establish this bathymetry. And you can see the cross-canal bathymetry. It's not simply dredged to a fixed depth in the cross. You have a bank and it comes down, and there's some very long canal variation as it goes. And these things, this is a dynamic system and it evolves. It's highly rigorous. The bottom's probably fairly armored at this point with a coarse substrate, but it's a rigorous enough system that you're going to have places that will erode, and places where you have deposition of the sediments, and the Corps has to ensure that the controlling depth is maintained through regular surveys and dredging, and they probably find themselves dredging similar places each time, just the nature of the hydrodynamics here. So you see the secondary circulation, which is interesting. And again, the pattern is it's always trying to head out at the surface. So this isn't a Coriolis influence. This is probably having to do with this 2.5 kilometer radius of curvature term here. And the acceleration of a fluid parcel right here in meters per second squared is just the streamwise velocity, about 2 meters per second squared. So that's 4 divided by this radius of curvature. So 4 over 2,500 is the acceleration of the parcel here. So tiny compared to gravity, but compared to other terms, particularly in the cross-flow momentum equation, it's going to be strong. It's strong enough to drive the circulation. Also, a pressure gradient and friction would be playing a role, but it's less easy to think about those. This last plot shows right here the kinetic energy flux, essentially the power potential from kinetic energy moving through a section of water right here. So if you were to capture all the kinetic energy, just suck it up to 0 as it moved through this plane right here, this is how much power you would capture. And power, of course, is energy per unit time. These are in kilowatts, so this is 4,000 kilowatts or 4 megawatts, and that's about the annual average power you're going to get through a transect of the canal, somewhere around 4 megawatts or 4,000 kilowatts. And you can see there's significant fluctuations which mimic these fluctuations of the spring, neap, larger spring cycle. You can see that in the power profile here. So on top of the twice daily variations, which produce powers in both direction, although there is some ebb flood asymmetry. You can see that right here. You have reduction during neap, and in addition a higher power during this spring, second spring tide here, a larger spring tide. And we have what you have to do is consider the full annual cycle. When you have strong neaps, or strong springs and weak springs and neaps, and the semidiurnal and occasionally a large perigean tide, you have to consider the full year and figure out what the average is over the year, or you want to consider in terms of energy the kilowatt hours that accumulate over a year. The nice thing about tides, of course, for power is it's completely predictable. It's quite predictable. A model could predict tides 10 years from now, whereas solar or wind power, you have about, wind power in particular, you have a 3-day prediction scale, maybe a week, to get something reasonable, and the sun depends strongly on your location. But in areas that do have cloud cover, you're talking about predictions of storm scale time, which is 3 days, 5 days. So this sort of long-term prediction means that the tidal power companies theoretically can sell their power at a higher rate because of the predictability of the tidal signal, theoretically, because we're really not quite there yet. All right, so I'm going to go ahead and run the model. You'll see this red triangle follows this with time, and you'll just see these things evolving, that the surface currents will switch back and forth, flood and ebb, along with the pressure gradient, essentially the sea surface elevation here driving the system. And there really is a sea surface elevation. So if you have 2 meters difference across this canal, you're talking about essentially 20 centimeters of elevation change. You know, you ride your bike along the canal, and every kilometer, essentially the canal is going up or down by 20 centimeters when you have a large difference between the two bodies of waters. I'm not sure you could see that, but that is really what's driving the system. So let me just go ahead and start this. Okay, so it should progress forward so that the difference between the tidal bodies of water near zero right now, almost zero velocity. And now we have a situation, Buzzards Bay is higher than Cape Cod Bay, and the water's reversed to flood. Now that flood is weakening, and we have near zero gradients, and we have Cape Cod Bay higher than Buzzards Bay. And again, so we turn back to a strong ebb situation. You'll see the secondary flow, it just weakens as the flow weakens, and we have low velocity, so we have low centripetal acceleration, and then it strengthens back again as the velocities increase, but it's always in the same direction. This will be flip-flopping direction from moving towards negative or ebb or Buzzards Bay motion, and you can see you have the strongest velocities tend to be in the core of the flow here, weaker velocities on the edges where you have stronger friction due to the shallower waters, and then you have bottom friction here, so the velocity technically goes to zero excuse me, at the bottom here. There's a little bit of asymmetry to the position of the max velocity in the channel. You can find other transects in the channel where there's stronger asymmetry, and it tends to have to do with excuse me, the cross-channel bathymetry, whether that's symmetric or not, as well as having to do with secondary circulation effects interacting between coming out of a bend into a straightaway, those kind of things. But essentially you have this sort of classic hydraulic flow situation. We're moving into the stronger spring tide. The pattern's the same, but you'll see a strengthening of the currents. So this will eventually get up to about 2.25 meters per second surface flow, and that's about the peak velocities that you see in this part of the canal at the surface. We're about halfway into this spring tide, and so when we move into the spring tide, that allows for larger differences to occur between the two bodies of water elevations. So associated with that are stronger currents. Associated with the stronger currents is this higher power potential during that time. But again, it's all relatively well predicted. All right, that about wraps up this segment. Thank you for watching.